Welcome back to this video on probability. This one is the third video now, and it is looking at tree diagrams. Now, a tree diagram can be used to show the outcomes of two or more events happening in succession. You should have a really good idea about tree diagrams from your IGCSE or GCSE courses. However, it's usually the latter part of the question where people or candidates struggle in S1. So the first parts are usually straightforward, pretty much GCSE standard. The final part of the question, usually a part C, is when you are using the given that formula, and that's usually where people make their mistakes. Now, if we have two events, so event A and event B in our tree diagram, A would be like this, A and complement of A, so A and not A. And we look at the probability of A to get to that first event and the probability of not A to get to that second event. Then if I think about coming off this, so heading then to my second event B, so that's going to be B or not B. But this isn't the probability of B now because A has happened. So this is the probability of B given that A has happened. And this one here would probably be the probability of not B given that A has happened. And the same can be said for the bottom one. So coming off my not A, I've still got B and not B for the complements, but this is now going to be the probability of B given that not A has happened, and the probability of not B given that not A has happened, because you're following on from a previous event. That's essentially what's happening. Now, if you remember from GCSE, when you go along your tree, along the branches, you multiply. So it's this multiplied by this. So if I think of the probability of A and B, then that's the probability of A multiplied by the probability of B given A, which is quite useful. And I can do the same for all of these, probability of A intersection not B, probability of A times probability of not B given A has happened. And this is because the second set of branches are conditional probabilities. They're based on the fact that either A or complement of A is what has happened first. So now I've kind of given you this bit of information, let's just jump into a couple of examples. So quite a lot of information here. Paul goes to work by bus or taxi. If he goes by bus, probability he goes to work by taxi the next day is this. And if he goes to work by taxi, the probability he goes to work by bus the next day is this. Given that Paul takes a bus on Monday. So what we're thinking is that on Monday, Paul takes a bus, and we want to get to Wednesday. So I think about the end of Tuesday, this point. So if he took a bus on Monday, so if he took a bus, probability goes by taxi is 0.4. So if he takes a taxi, this is 0.4, which means that if he doesn't take a taxi, is 0.6. as the probabilities must total 1. Sorry, just give myself a bit of room there. Then coming off the taxi, if he takes a taxi to work, where are we? So if he takes a taxi to work and he goes by bus next, then that's going to be 0.7. So bus and not bus, so 0.7, 0.3. as again, these must total 1, isn't it? So if he takes a taxi, it's 0.7 that he takes a bus the next day, which will be our Wednesday. Now, I need to finish off the bottom bit. So if he doesn't take a taxi, okay, that means he's taken a bus, isn't it? Yeah, and from bus we know, again, I can write it like this, but from a bus we know it's a 0.4 that he takes a taxi and 0.6 that he takes the bus. Because that comes from down here. You know, I've used two different symbols, but the reality is that, you know, this is the same as not bus, and bus is the same as not taxi. So I guess the point is, in a question like this, maybe it's better that we don't use symbols. Maybe it's better to use words. Taxi, bus. If I'm looking up here, this was bus and taxi, and these were the same, weren't they? Bus and taxi. So maybe in this kind of case it's better to use words. Now we've got to find the probability that he takes a taxi to work on Wednesday. So we want this scenario and this scenario. So this scenario happens this way, 0.4 times 0.3. So this is like the probability he takes basically 2 taxis on both days. So 0.4 times 0.3, 0.12. And my second scenario is that he takes a bus, then a taxi. So that's the probability he takes a bus, then a taxi, which is 0.6 times 0.4, which is 0.24. Now, the probability that he takes a taxi on the second day is this happening or this happening. So the probability taxi on Wednesday is 0.12 plus 0.24. When you do an or, remember you're adding your probabilities. And that's it, and that's our nice straightforward starter example. Now in the second question, again we're going to use travelling. So it's car, bus, train, so 0.1, 0.6, 0.3. And then it's late, which is going to be late or not late. And the first thing we need to do is a tree diagram. So for part A, we've basically got 3 options, haven't we? We've got car, bus, and train. And these are 0.1, 0.6, and 0.3 respectively. The probability of being late when using these methods are, so coming off here, we've basically got late and not late. So maybe L and not L. To make it a little bit easier. So from the car, probability that they are late is 0.55. Probability that they're late from the bus is 0.3, and probability they're late from the train is 0.05. And then I've obviously got to, each one is going to add to 1. So we've got to have 0.45, 0.7, 0.95 there. And there's my Venn diagram done. Now, part B1 says the probability that he travels by train and is late. So that means he's traveling by train and is late. So 0.3 times 0.05. and that is 0.015. Part 2 says that he's late, so the probability that he's late. So that's going to be this path, so 0.1 times 0.55, or we could take the bus and then he's late, so 0.6 times 0.3, or we could take the train and then he's late, which we've already worked out, but I will put it down like so. Now all I need to do is work this out, and this will give me 0.25, which is a quarter. Nice. Now part C says, given that Hussein is late, find the probability that he did not travel by car. A little bit difficult this time, because the given that is starting from the lates and working this way. So not so straightforward. So we're looking at probability that he didn't travel by car, so we want not car, and we want the fact that he's late. So we want the probability that he didn't travel by a car and is late over the probability that he is late. And this is using your formulae. So not car and late means we're using bus and late, train and late. So those we'd already worked out, hadn't we? Bus is late is 0.6 times 0.3, which is this 0.18. And the probability the train is late is 0.3 and 0.05, which is this one, or 0.015. And then that's going to be over the probability that he's late, which is this 0.25. And that's then when I go to the calculator, so 0.18 plus 0.015 divided by 0.25, and that gives me 39/50, or 0.78. This particular part C here, this is the bit where people go wrong. This is generally the part where you've got a given that, where it's going as if you go in the opposite way, because given that going this way is easy, because like the probability of being late, given that they're taking the car, is just 0.55. That's what we already, when I wrote on the algebraic one at the start, but it's when it's given that a value from here, when you kind of need to go this way, that's where people get confused and make a lot of mistakes. So that's when the formula's got to come into play. Now, what I've done here from this question onwards is 6 questions in total. I picked them out from some older past papers, but they were all questions where people had a little bit of an issue, usually with the latter part of the question. Don't forget to pause the video and try the questions before you see the answers. So let's get started with this first one. So the first steps are to complete the tree diagram, which isn't too difficult. We've got 7 red counters, 3 blue and 2 yellow. And I'm just leaving these 2 unsimplified just initially. Now, since she takes a counter from the bag and keeps it, that means as we go on, it's conditional probability. So, if I follow on this red one, she's taken a red, so there's now 6 reds. So this is going to be 6/11. But we still have 3 blues and 2 yellows. And just double checking, 6, 3 is 9, 10, 11. These should always add up to the same as the bottom value. Now, if I take a blue one, then I've got 7 reds left. I've only got 2 blue left, and I still have 2 yellow. So that is my 7, 9, 11, so it works. And that is then my tree diagram done. Now, the second counter, at initial looking at it, okay, it looks a little bit confusing, but it's not. Okay, given that Gina has selected a yellow counter, find the probability that she has 2 counters. So that means she either selected a yellow counter straight away, because it's given that, or she's ended up like, say, red and yellow, or blue and yellow. So we're looking at probability, so it's probably that she has 2 counters given that they are yellow. That's probably the best way of setting it out. So it's probability of 2 counters and yellow over the probability that it is yellow. So 2 counters and yellow is what I was saying, red, yellow and blue and yellow. So that is red and yellow plus blue, which is 3 over 12, and yellow, which is 2 over 11. And then the probability that we have a yellow counter is very similar, but it's 7 over 12 times 2 over 11. It's that yellow. That one's yellow, isn't it? But then also we could have just had a single yellow counter, couldn't we? Straight away yellow counter. So all I need to do now is a bit of simplifying. So on the top I get 20 over 132. Again, I haven't simplified because it makes my life a lot easier, you know, with the same kind of bottom or denominators. And there we have my final answer with a bit of simplifying. Hopefully that wasn't too bad a start for you. So part A in this question is just, it's not as quite straightforward, but when you're looking at it, he takes a ball from bag A, puts it in C, takes a ball from bag B and puts it in C. So here we've got our A's and we've got our B's. So the probability that he takes a red ball from A is 4 over 6, or you can see it's here as 2/3. So getting a yellow ball is 1/3. We know that, don't we? And following on here, this one's got to be 1/5, because they've got to add to give me 1, don't they, across here. So if I've taken a yellow ball out and I've popped it in the end, in bag C, then looking here in bag B, you know, we've got 4 red balls, 1 yellow ball. So that's going to be the same, isn't it? 4/5 and 1/5. Okay, and all I'm left to do now is add my remaining branches here and fill in those values. Now what we want to do is just work it out. So if I've added 1 red in here and a second red in here, it started with 6, it now contains 8 red balls. So we've got here red, there's actually going to be no yellow, so I can actually probably get rid of this actual branch there. So, you know, the probability of this is just 1, isn't it? 8 out of 8. Now looking at the second one here, we've got red, then yellow. So that means we go to 7 red, 1 yellow. 7 red, 1 yellow. Just put my red and yellows in for the next line. Then looking at the next one, we've got a yellow and a red. So again, we're going to have 7 red and 1 yellow. And then looking at the final 2 here, we've got yellow and a yellow. So we've got 2 yellows. So the probability will be 6 over 8 and 2 over 8, because we'll have 6 reds and 2 yellows. And that's my tree diagram drawn. Now, before I go any further, what I would say as well is that sometimes it's easier to work out the probabilities at the end of each line. So, you know, like here I've got 2/3 times 4/5 times 1, so that's 8 over 15. And then here we've got 2/3, 1/5 and 7/8. So 2 times 1 times 7 is 14. And 3 times 5 times 8 is 120. And I'll leave that bottom value the same as then, it's just nice for the others. Look, 2/3, 1/5, 1/8. So that's just going to be 2 over 120. Then we've got 1/3, 4/5 and 7/8. So it's going to end up being 1 times 4 is 4. 4 times 7 is 28. So that's 28 over 120. We've got 4 over 120 there. Then we've got 1, 1 and 6, so 6 over 120 there, and 2 over 120 at the end. And checking all these out, you can add them all up. This end one is equivalent to 64 over 120. But if you add these up, 64, 14, 2, 28, 4, 6 and 2, you total 120. So you know I've done it right. Now that can make my life a bit easier sometimes when I'm looking at later ones. So show that the probability that Mike records a yellow ball exactly twice. So that means that Mike could go red and then 2 yellows, or, because that's red, yellow, yellow, yeah? Or you could go yellow, red, yellow, or you could go yellow, yellow, red. And that's the way he's going to get exactly 2, isn't it? So following red, yellow, yellow, red, yellow, yellow is 2 over 120. Plus, following then yellow, red, yellow, yellow, red, yellow is 4 over 120. And then finally yellow, yellow, red, 6 over 120. So that gives me 12 over 120, which simplifies to 1 over 10, as required here. Now, part C says, given that Mike records exactly 2 yellows, find the probability that the ball drawn from bag A is red. Okay? So we're looking at the probability that it is red from A, given that there are 2 yellows. So we're looking at probability of red from A and 2 yellows over the probability that we get 2 yellows. So red from A and 2 yellows is this one, wasn't it? 2 over 20. Sorry, 2 over 120. And the probability of 2 yellows is 1 over 10. Okay, or you can think of it as 12 over 120, which you know might be easier for you. But this then should give me 1 over 6. Now, part D, we're moving on a little bit, so slightly outside of the normal box, but we're going into PDFs, probability distribution of X. And it is about how many yellow balls are recorded in a single game. So for this, we know we're going to have X, and we know that there's going to be a few scenarios. The first scenario would be that there are 0 yellows chosen if they were all 3 red. Second scenario is 1 yellow. The third scenario is 2 yellows. And the final scenario is 3 yellows. So these are the only possible scenarios. Okay, and then all I want here is my probability. So I'm just going to tidy this up. And here is my probability. So probability of 0 yellows. So that is the same as the probability of red, red, and red, which is 8/15 or the 64 over 120 there. So let's pop that in. 64 over 120 or 8 over 15. Now, 1 yellow means we go red, red, yellow, which isn't a scenario, is it? Okay, but we can go red, yellow, red. So that's one possibility. So let's go like 1 yellow. So that could be red, yellow, red. Or if we start with yellow, it would be yellow, red, red. Just 28 over 100. So yellow, red, red. These are the scenarios. So red, yellow, red was 14 over 120. Yellow, red, red is 28 over 120. So that you can see there gives me 42 over 120, which will simplify to 7 over 20. 2, obviously we've got that answer there, so we can just pop that straight in as our 1/10. And 3 is just 3 yellows, so the probability of 3 yellows is just my yellow, yellow, and yellow, isn't it? Which is 2 over 120. So that's 2 over 120 or 1 over 60 there. Nice and easy, I think. So there's my probability distribution of X. E is fitting, find E of X. And all I've got is 0 times this, 1 times this, 2 times this, 3 times this. Okay, dead easy, nothing too difficult there. What I would say is with the 2, if you change that into, your 12 over your 120, because now all of these would be a fraction over 120, you could go and take 120 out and just do like 0 times 64 plus 1 times 42 plus 2 times 12 plus 3 times 2 and did it that way, and then you've just got 42, 24 and 6, so 30, 72. So suddenly we get 72 over 120, nice and quickly, and 72 over 120 is 3/5 or 0.6. So obviously that's a little bit of a shortcut, and that's why it's nice to do it in terms of the same bottom number, the same denominator. But obviously if I didn't do it that way and I did it the standard way, we would be 0 times, say, 8/15 plus 1 times 7 over 20 plus 2 times 1/10 plus 3 times 1 over 60. Yeah, so you got 7 over 20 plus 1/5 plus 1/20. And that will, of course, get me my 3/5 or 0.6. Okay, so, two kind of ways there for that final part. Hopefully that helps you in the future. So first part here, fill in the tree diagram. So we can see there are 5 red balls and 7 blue balls. So it's got to be 5 over 12 and 7 over 12 there. Now the question goes on and says, when a red ball is selected, a biased coin is thrown, and it's 2/3 chance landed on head. So red, so this is going to be 2/3 and 1/3. But it's a fair coin if the blue one's spun. So this is going to be 1/2 and 1/2. And there it is, nice and quick and easy. Now for part B, we've got Shivani, and she gets a head. So the probability of getting a head. So this is, we could have gone red, then head, or blue, then head. So red, then head is 5/12 times 2/3. Blue, then head is 7/12 times 1/2. And that gives me 41 over 72 there. Now you can see as we move on to C now, we've got a given that. Given that Tom selected a ball at random and obtained a head, find the probability that he selected a red ball. So this is now part C, probability he gets a red ball, given that he gets a head. So this is probability of red and head over probability of head. Let's pop this up there. So red and head means red and head, 5/12 times 2/3, which we've already done up here, 5/12 times 2/3, so it's 5 over 18. But I will pop the 5/12 times 2/3 there, which we know is 5 over 18. And then on the bottom, it's the probability of getting a head, which is this, 41 over 72. And that gives me 20 over 41. So that should be quite nice and easy so far. Let's move on to D. Shivani and Tom each repeat this experiment. Find the probability that the colour of the ball Shivani selects is the same colour of the ball that Tom selects. Strange part D, but here we go. Same ball colour. So that means that they both either choose red or they both choose blue. The probability of them both choosing red is going to be 5 over 12 times 5 over 12, isn't it? Because it's the probability of Shivani choosing red and Tom choosing red, so it's multiplied. Plus for my OR, and then the same thing for the blue one. And that will give me 37 over 72 there. What an easy 10 marks, I would say. Now you can see this is very similar to one of the examples, and it's clearly a past paper question as well, which means there's some similar past paper questions that have shown up. So he goes by car, bike, or foot. And then he's either late or not late. So car, bike, foot. Car, bike, foot. Late, not late. Late, not late. Late, not late. I'll just fill this in for you quickly. And remember, when you're doing this, then these two will have to add up to 1. And there we have our tree diagram. Now, part B is find the probability that Bill travels by foot and is late. So foot and late, we've got 1/3 times 1/10, which is 1/30. And part B is that he is not late. So not late is that he goes by car and is not late, or by bus and is not late, or by foot and is not late. And that gives me 4/5. Now you can see here part C is the given that. Given that Bill is late, find the probability he did not travel by foot. So for part C, it's given that he's late, he didn't travel on foot. So not foot, given that he is late. Okay, so the probability of traveling on not by foot, so that would be probability of not foot and late over the probability of late. So not foot and late is going to be 1/2 times 1/5, as that's car and late, or 1/6 times 2/5, as that is bus and late. And then the probability that he is late is actually using B part 2's answer, 1 minus the probability that he wasn't late. That gives me 1/6 on the top and 1/5 on the bottom, which is a probability of 5/6. Now, this is the last question. I did say 6 questions, but realised that one of them was actually a Venn diagram question, so I took it out. Now, first part of this is to draw my tree diagram. Let's do this underneath. We've got, in a factory, machines A, B and C. So we've got A, B and C. And they're all producing metal rods of the same length. A produces 35%, so 0.35. B produces 25%. And C produces the rest, which will be 40%, so 0.4. Now it tells us that of the production of rods, machines A, B and C produce 3, 6 and 5% defective rods. So this is going to be defective and not defective. And there you go, just sped up a bit there, and here's our tree. Now, let's look at part B. Find the probability that a randomly selected rod is produced by machine A and is defective. So A and defective, so AD, that's what we're looking at. So 0.35 times 0.03. So that's 0.0105. Part 2 is defective. So that means that it could have been from A, or it could have been defective from B, or it could have been defective from C. So that would give me, well, 0.0105 for my first one, and then BD is 0.25 times 0.06, and then CD is 0.4 times 0.05. Sorry, I'm running out of room on the side here. Let me make some. And that gives me 0.0455. Very straightforward, just like all the previous questions. Part C now is where we've got the given that. Given that a randomly selected rod is defective, find the probability is produced by machine C. So we want C, given that it is defective. So it's C intersection D over the probability of D. Remember that this first one, or what was it, B part 2, was the defective one. Just make it a little bit more clear there. So we got C and D, so that's C and D. So it's the 0.4 times the 0.05. 0.4 times 0.05. This is going to be over our answer to B part 2, so 0.0455. And that gives me 41 over 91. So roughly 0.44 there. Okay, but easier to keep this as a fraction since, you know, it's not a terminating decimal there. Hope you found this video useful, and stay tuned for the mixed probability past exam questions that should be coming later on today.